Welcome everybody to our second talk for the June meetup. This is by Italo Vietro and it's about designing for failure in Go. The stage is all yours.
All right, thank you, Natalie. Hello everyone. My name is Italo and I am from Brazil. I'm currently working as a CTO at Lykon. Lykon is a med tech company here in Berlin. We do lots of Go, we do lots of Kubernetes and Istio. And because of that, we also have a lot of distributed system going on. And if you're familiar with distributed systems, which I assume you are, because in these days, there's not really a way to go, further away from it. We are always exposed to failure. Like in a distributed system setup, you always can, things can fail very, very quickly. So what can we do as developers to avoid such failures? What can we do to actually design systems for the unexpected? So today in this talk, I'd like to go through a few patterns that I tend to use, and also I see the community using quite a lot, which helps us actually build software that is a little bit safer, that is actually ready to fail. So in the agenda today, we're going to talk about what is resilience in the first place. We're going to talk a little bit about latency control, isolation, self-healing, traffic control, observability, and then in the end, we'll talk about service meshes. So before we get into that, I'd like you to think about a plane, right? Think about a plane right now, or like if you never flew in a plane, just think about the machine itself. If you put into numbers, last year in 2019, we had about 39 million flights happening across the world, which is quite a lot. It's a huge number if you think about it. Of course, this year is going to be affected by the corona situation, but in the end, that's the average of flights that happen every single year. And last year was one of the records in the world where we had 39 million flights, which is huge. But unfortunately, out of those, we had 23 deadly crashes and also 28 fatalities overall. It seems like a small number, right? But still, people lost, people overall. Families lost someone that was loved. And out of those numbers, we actually had one that was confirmed to be a software failure. One which I think most of you are familiar with, the MAX, 737 MAX situation that happened in the US with Boeing, which was a mix between software failure and also a human error. But essentially was because someone coded a software that had no way to override it, right? Like when a problem happened, nobody could override it. So one fail in 39 million flights, one fatality that happened because of software, it's actually pretty okay. But if you think about it, softwares that were designed to fail, they actually can be way more reliable. So in an airplane, software fails all the time. Airplanes fail all the time. You just don't notice. Like a lot of times, I'm pretty sure if you fly a lot, I'm pretty sure something already happened that was critical, but you couldn't see it. Because software for airplanes or electrical engineering and mechanical engineering were created for such a resilience in the airplane, because you're carrying lives, that you had to have strategies to actually fail, right? So if you think about an airplane again, think about a battery. And airplanes have at least 7 batteries. If one fails, they will fall back to the next battery, the next battery, and the next battery, until there is no electrical battery. And then they actually fall back to the mechanical way of doing things, where a fan drops down the airplane to actually generate energy from mechanical movement, from contact with the air. And that's really amazing. That's how I like to see software. Like when we design software, we can make things more reliable. We can make things more safer to use. And all of that in the airplanes is created by something called electrical load management system, which is ELMS. And the key here is that it keeps the essentials running. Like this system was designed to keep things that are essential to run. So think about your software today. Can it actually continue to run if things fail only with the essentials? And that's what I'd like to bring up today for us to discuss a little bit and also show a little bit of the patterns that are there that you can actually use. So I like this quote quite a lot. Resilience is a requirement and not a feature. So by Liang Guo. And this is super important, especially when you're talking with product people. You know, a lot of our discussions as leaders and as technologists is to actually make sure product understands that resiliency. It's not something that can be neglected. It should be embedded into every single product feature that we deliver. And although this might be a super hard discussion to have with product owners or the product team, it's something that we have to go through. And the value that you're going to bring to your customers is huge. So it's something definitely to consider. So I like to start with latency control. Like we're going to go through a lot of different patterns, and a lot of those are going to be so obvious to you, but I'm going to give a name to it. And a lot of those you might not even know. And I hope this talk will be a little bit enlightening for a few people. So let's start with latency control. And the most basic thing that you can start with is timeouts, right? Think again about your application. Think that you have different dependencies that you call every time. You call your database, you call an external service, you call a third-party API. And a lot of the times we just use the default Golang, Golang client, HTTP client, where you don't really have timeouts set out of the box. So definitely something to consider when doing client timeouts. It's to simply set the timeout, right? Like this is a starting point. You can set a timeout. You can then create a request where this website here just simulates delay. And you can call actually the website and then it times out, right? It's going to time out. It's going to return an error. And then you can handle that error. You can do something with it. If it times out, you can actually, retry the request later on, or you can throw an error to your user or whatever. You just be sure that you tell something to your user in the end. So Go, it's super nice because then it gives you this possibility of, configuring the timeouts. And actually you can go much deeper into that. You can actually configure timeouts to be a little bit more specific. You can go even to the transport layer. And you can do, the dial timeout. So the timeout and the keep alive. You can go to the TLS handshake timeout. You can be very granular here and there. If you're doing TCP and not HTTP, so you're in the layer 4 instead of layer 7 of the HTTP, of the networking layer, you can also use timeouts, especially in TCP connections. So super important, if you don't use timeout today in your clients, and if you have an external party or even an external dependency from your system, please start using timeouts. It's going to give you like such a peace of mind. But handle it, right? Don't just use it. You have to handle the error when it happens. Then we also have a different thing here, which is a different way of configuring timeouts. So Go has context, as some of you already know. And you can have context with timeouts. And once you use, like in this example right here, I'm setting a timeout of 2 seconds in the context. And then I'm creating a request with context, where I pass the context here. So what happens here is that if the request is not fulfilled within the 2 seconds, we're actually going to get a cancellation. We're actually going to be like the context will cancel, and then you can actually propagate that cancellation across your application, which is great. So you can, for instance, if you're having multiple calls, if you're calling in parallel, you can actually cancel all the other requests because you know they're going to fail if they're pointing to the same place. Or you can do other things. You can handle cancellation in different ways. You can close connections. You can reset connections, etc. So there's a lot of possibilities here. I really like when Go introduced the new request with context. because it gives you the power to do this without, being hacky, trying to do that in the other way. It's super explicit. Yeah, so client timeouts, great start. But let's say that you're writing an API or any HTTP server. The HTTP package actually offers you, when you're creating a server, to actually set up your timeouts as well. As a server, you must set up your timeouts so you don't keep idle connections or hanging connections taking resources out of your application. So this is great. You can set up read timeouts, write timeouts, idle timeouts, reader header, which is the first step on your, or one of the first steps when establishing the HTTP connection with your server. And you can actually have those timeouts set, and figuring out those numbers, it's what's going to be hard for you. At least it was very hard for me figuring out numbers. These here are just arbitrary numbers, but in a real life application, what you really want to look at is your metrics and understand what exactly is your timeout number to put here when creating a server or when creating a client. So definitely use server timeouts. It's going to help you out. It's going to make you, it's going to make your server more reliable. There is going to be a link in the end of this presentation for a very good post in the internet. I forgot by whom, but they actually explain the difference between timeouts, server timeouts, client timeouts, and how can you configure this in your application as well. Cool. So again, latency control, server timeouts, we finish here. And then we jump into circuit breaking. So circuit breaking, it's not exactly latency control by itself. Circuit breaker by itself doesn't do much, right? So again, if you think about electrical engineering, every house normally has a circuit breaker. You've probably already seen it. You probably already faced a problem with it. If there is a problem in your electrical circuits at home, normally something triggers or a circuit opens, and then it avoids getting fire or something like that. The same principle is applied here in software engineering. I like circuit breakers quite a lot because the way you can do it in Go, there are many libraries that you can use. You can build your own. I don't recommend doing this because you don't want to reinvent the wheel. But there is a really good one called Go Breaker, where you just create a circuit breaker. So you give it a name right here. And you pass a function ready to trip, which is going to be called every time something trips. And a trip means, a failure happens within an execution. So if you look at this block down here, I'm encapsulating an external call to Google. And let's say that Google, for whatever reason, returns me a status bad request. If that happens, this function is going to be called. And this function is expecting a Boolean as a return. So here, I'm creating a failure ratio. So there are many ways for you to actually configure your circuit breaker. So here I'm saying, if more than 3 requests fail, and the failure ratio is bigger than 0.6%, 6%, like 0.6, then actually just open the circuit. When you open the circuit, every single request that is going to Google, it's going to stop going to Google, so we don't overload their servers. Don't think about Google. Think about something simpler, probably. But we don't want to overload the upstream server because we want to give time for the upstream server to breathe and to actually fix that problem before we call it in the next time. And that's a point of circuit breaking, right? We don't want to overload something. Again, electrical engineering, when the circuit opens, is for avoiding the wire to actually get fire, becomes so hot that it burns. So it's the same principle right here in software engineering. So circuit breakers were enhanced by, I saw there were some people here which came from Java. And if you came from Java, you're probably familiar with Hystrix. Hystrix was a pattern developed by Netflix, which is now discontinued. It was deprecated. But the pattern itself, it's really cool. Like they had a library and all, but the pattern is basically saying how you can have different circuits in your application, how you can encapsulate them in a standard way across multiple JVM services. This pattern was implemented in Go. So if you look in Google, if you search in Google for like Hystrix Go implementation, you're going to find some implementations out there. But Hystrix was discontinued, and I'm going to explain in the end of this presentation why. Yeah, so Hystrix, here's the dashboard. It shows you like super useful information about circuits that are open or closed, and you can react to it. You can do something. But if you think about it, circuit breakers, as I mentioned before, they're not, they're not very useful by themselves because they're going to open the circuit. Cool. How do you close it again without touching the service? There are many different ways you can do this. One that I like is doing retries. So we have this sequence diagram over here where you have a consumer service and you have a producer service, right? So you're going to call that producer service. So the execution stack is basically going through execute the request, wrap around the circuit breaker, execute the request, wrap it with a retryer, and try to call the producer. In our case, it was Google. So I'm trying to call Google, and if it's not successful, I'm going to retry and retry and retry until a threshold or until whatever rule I put to stop trying again. So because sometimes in a distributed system, you're going to have network hiccups. You're going to have latency issues. You're going to have some other thing that is unexpected to happen. And, sometimes they happen and they're gone, and you can retry and it's going to work. So you really want to automate that process. You don't want to, interfere every time something bad happens into your network. So right here, we have a very good library from Avast where they have this retry, which is super simple and super good. You just have to wrap around whatever call you're making. This could be a database call. This could be an HTTP call. This could be a TCP, gRPC call, whatever you like. And, you just encapsulate it. You get a response, and it's going to retry for you if there is any error being returned here. It's going to retry up to a point. In this point, I'm going to retry 3 times. But, there is also a different thing here. Like when you retry, if you don't specify a delay type or whatever delay you're doing, if you don't have a delay between the retries, this execution is going to be super fast, one after the other. And the service will still fail because it was just too fast that it didn't really fix it. So you can have something called, back off. And when you have a back off, when you have an offset limit where you just put some delay here that multiplies by 2 or by the value before, you can actually give some time for the service, for the upstream service to breathe, and then it tries again automatically. So you don't have to handle this, which is great. That's what you want to achieve. So yeah, retries, really good stuff. It really helps when you're, dealing with external calls, especially third-party APIs that you really depend on. Cool. So let's talk about isolation now. So we talked about latency control. Let's talk about isolation. So isolation, what do you want to make sure here? You want to make sure that your service, if it fails, it has to be failing in isolation. So there is a standard from the naval industry. It was created in the naval industry called bulkheads. I believe all of you are familiar with the Titanic. And Titanic, I think, set ship on, I think it was 1912 or something. And as you know, it sank, right? It hit an iceberg and it sank. But if you think about it again, there was a design. If you ever saw the movie, there was a design failure, right? And there's a lot of papers in the internet that you can read about it. There was a design failure, and the design failure was in the bulkhead. So this is supposed to be a GIF, and so if you see these yellow lines right here, those are the bulkheads of the ship, right? A bulkhead, by definition, is supposed to isolate something. Something happens and it isolates that. So the bulkhead here was supposed to isolate the water coming into the ship. Unfortunately, as I said, there was a design error. And the design error was when the water filled up more than 4 compartments, the water was passing from one bulkhead to the next bulkhead by the airflow that they had to pass in the chambers over here. And because the weight was so big, of course, the ship cracked in the middle, and then it just sank. So yeah, the book had a design failure. But the interesting thing is the learnings that the naval industry got from this event. And they actually try to improve the book head definition. Uh, in software engineering, we also use book heads quite a lot. Again, Hystrix implements book head by default. How can we do it in Go? So in Go, everything that you want to try to do, if you're doing external calls to your third-party providers or to databases or whatever, if you encapsulate that in a Go routine, then you can do concurrent calls. You're going to have a lot of them happening because you receive a lot of requests, and they're going to be encapsulated. If one of them fails, the Go engine itself, it's not gonna fail, right? Like your application is still gonna run. If you think about Java, that's the thread pool, and the thread pool, you can have one thread that fails, but the other ones are still running. And the same way you can do it with Go, you can replicate that pool. There is the sync pool, which works in the similar way. But if you replicate that pool of connections, you're actually not gonna have one request stopping all the other requests unless you use a context for this. So book heads are pretty cool. And I'm going to leave a link in the end as well for a Microsoft documentation about it. It's really great. I recommend you to read it. So if we talk about self-healing now, right? When problems happen in your application, you want your application to self-heal, or to the best that it can. So because of self-healing, the first thing you want to do is actually make sure your application has health checks. So if you don't have health checks by today, maybe consider adding one. There are different kind of health checks. In this case over here is very Kubernetes specific, but still can be applied to any kind of load balancer like Nginx or HA proxy or whatever you use. So normally in Kubernetes, we have liveness checks and we have readiness checks. The readiness checks are important things for your application to be ready, like your database, like, I don't know, an external payment service or Google in this case. The liveness check is going to check your application's health, and it's going to notify, specifically Kubernetes is going to notify the scheduler to say, hey, there is something wrong with this pod, do something about it. But regardless of Kubernetes or something else, you can have health checks that actually check for dependencies on your application and notify load balancers to kick you out of the load balance and bring up a new one. So in an example, if you call that application right now, and if you do like localhost 9090 in this case /live, and if things are okay, you're going to see an okay right here. If you call /ready, you're going to see an okay over here. So pretty simple, pretty straightforward. Now, if things are bad, you're going to get a 500, like a 503, and you actually going to see the reason why, right? Like in this case, it's just like this host doesn't exist. So yeah, and this 503 here is going to actually tell your load balancer to do something, right? It's going to tell, hey, kick me out of the load balancer. So pretty good stuff. I recommend you to use it. Yeah, it really helps. I'm just rushing a little bit here because there's a few minutes left, but the outboxer pattern, also another pattern that is really good. If you think about external dependencies again, right? If you think about Kafka, for instance, which is your message broker, or RabbitMQ, if you use that. Sometimes producers of messages don't think that RabbitMQ or Kafka can go away, because in theory it shouldn't. But it can, right? Like, let's say that your Kafka cluster or your RabbitMQ cluster, they are just out. So what do you do with those messages? Do you drop them? Do you lose them? In that case, the outboxer pattern is something really interesting to use, but also very controversial. When your AMPQ in this case, right? Let's talk about RabbitMQ. When RabbitMQ is down, what we're telling here, this is a library that actually does outboxer for you. So you just have to declare your main storage. In this case, I'm using Postgres, your broker, which is AMPQ in this case, and then we wrap it around with Postgres instance, and we create an outboxer. So here we're saying, okay, I'm going to use that data store, I'm going to use the RabbitMQ connection, and I'm going to check the interval. So I'm going to check every second, if RabbitMQ is up again, and then I'm going to send all the messages to there. In case RabbitMQ is down, this library will save the messages into a primary store, which is Postgres in this case, and then it's going to retry again to send to RabbitMQ once it's back up automatically, which is great. Like this is basically what happens, right? Like here we're going to send a message, and it's going to make sure if RabbitMQ is not there, it's going to put it in your data store, in your primary data store. If it is there, it's going to just send as normal. So yeah, if you want to check it out, like this library and some other documentations, is a library built by me, but feel free to look in GitHub. Cool. Traffic control. That is a pretty simple one, but very neglected one as well. We got rate limiting. Rate limiting is something that is so old that is there, but we never used, at least I wasn't using that much, right? When I start building APIs, I don't know, like 10 years ago or something, I didn't even consider rate limiting. These days, of course, I consider way more, especially when building public APIs. So in Go, there is a lot of different ways for you to do rate limiting. One that is super cool, it's in-memory rate limiting, which is cool if you have a single machine or a single instance of your application running. You can use this very cool library from whatever this pronounce it, Ulule, I think, limiter, where they have a different, like they have this memory store, and you can have actually like middlewares, which is super nice. But the problem really arises when you have distributed rate limiting, when you have more than one instance of your application running. In that case, you're going to need some sort of distributed storage so you can actually aggregate the counting and then move forward. In this case, this library also got you, and you can set up a Redis, a Redis client that will help you out. Cool. Observability. Nothing that I set up to now is useful if you don't have observability in your infrastructure. We always start using metrics. Metrics is probably the most basic kind of observability you can have. And if you ever heard about open census, I definitely recommend you to look at it. So yeah, you can have like something like Prometheus here. All of these examples are going to be in the end, so you can check it out later. You can also have distributed tracing, which is going to give you exactly what are the stack that your application is passing through, so you can actually look at it. Again, some sample here, easy to configure, standard to configure. That's the beauty of open census and open tracing. And this initiative between open census and open tracing has become something called open telemetry. And it's coming soon. It's already in the beta version. Really good. I definitely recommend you to look at open telemetry. They're doing a very good job over there. So as you saw, this is a lot of things, a lot of different concepts to actually implement on a simple service that you're building, right? Not everybody has, if you have one service, that is fine. You can just implement those things. If you have 100, well, you're going to start reconsidering. And that's when service meshes actually start coming up. So here, I'm just getting an example with Istio and Kubernetes because it's the one that I have more experience with. So the way Istio works, simple, very simple and quick explaining. You have a sidecar proxy. You have another sidecar proxy in every single application that you have. And every request that is coming in or out of your application is going to go through the proxy itself. And the proxy will handle a bunch of things for you. One of the things, as I can show you right here, is the timeouts that we discussed in the beginning. So easily you can set up a virtual service in Kubernetes or in Istio and set up, okay, every call that I'm going to do to this service, I want to set a timeout. I want to set a 10 seconds timeout. And in Go, you don't need to set the timeout anymore, right? In theory, you don't need to do it because the request will fail after 10 seconds. The same is valid for retries. If you use retries, right here, I'm doing the same logic that we saw before in Go, but I'm doing in Istio. So I can clean that code in Go and then start using Istio for it, right? And it's going to handle that for me, which is great. Same thing with circuit breaking. I can have a destination rule, and we can set a little bit of a, like some rules here for circuit breaking. And that's how it goes. And Istio also gives you a super nice thing that you can visualize your mesh, basically. So you can see where the request is going, to which services and which versions of your application is going, which is amazing. I definitely recommend you looking into service mesh. There is a lot of controversy in service meshes. Some people like, some people don't like. I'm not here to say if it's good or bad, just saying it really helps when you have a distributed system. So just to recap, I am already a little bit after my time. So just to recap, we saw what resilience actually means from the airplanes and naval industries. We have seen a little bit of latency control. There is a lot more into this to put in a talk of 30 minutes. Isolation, we saw a little bit of bookheads, self-healing, traffic control, observability, and service meshes. So again, if you want to check out other talks that I have, please check out on GitHub. There is an example called Coffee Shop. I'm a very good, I really like coffee and I'm very addicted to it. So I did this service, which is completely resilient and is actually using most of the patterns that I use here in Go. If you want to study a little bit more, I recommend you looking into this link from Microsoft. Really good stuff. If you want to find me on Twitter, please feel free to do so. And I really appreciate your time over here. Thank you very much.
Thank you for the talk.